Okay, now let us try to find the solution for the problem given. Here, a circuit is given in which there are two switch positions. This is a switch that can attain contact with one or position 2, one at a time. Position 1 or position 2 at a time. It is also indicated in the circuit that a current I of t, that is flowing in clockwise direction. Okay, now let us try to read the question and try to understand what is our problem and what is to be calculated. Okay, for the circuit shown in figure, determine the resultant current I of t. Okay, this is I of t. We have to evaluate the current. Okay, when the switch is moved from position 1 to position 2, when the switch is moved from this position 1 to position 2, initially the switch has been at position 1 for a long time. Means previously the switch has been at position 1. These are the clues, and we need to be concentrated more about these points. Initially, the switch has been at position 1. Because now, let us draw the circuit diagram in which initial state is indicated. Means when the switch is at position 1. And this is the situation when the switch was at position 1 for long time. That is to be noted. For long time means to attain the steady state, because when the moment when we put the switch into position 1, the current flowing through this circuit will be 0. Why? It is because of the property of the inductor known as self-inductance. Due to self-inductance, the moment when we closed the switch, or the moment when we put the switch into this contact position 1, the starting current will be 0, because inductor opposes the sudden flow of current. That property is known as self-inductance. Sometimes the inductor starts to store energy in the form of magnetic energy. Okay, then the current starts flowing, and the initial current of course should be 0. Graph may be like this. Starting current will be 0, then gradually the current will build up, and after some times, the when the inductor is fully charged, okay, then the current can easily flow through the circuit, and at that moment when the inductor store full energy inside it, then inductor offers zero resistance to the flow of current. Means when the inductor attains a steady state, then the current flowing through this circuit will not have any effect on the inductor. Otherwise, we can say that the resistance offered by the inductor will be 0 when the inductor is fully stored with magnetic energy. Okay, right. Then the resistance will be 0. The only resistance in the circuit at that time will be this 4 ohm resistance. Means after some times the circuit will look like this one. No inductance, no more resistance. Okay, here only resistance in this circuit is the resistance offered by the 4 ohm resistance. Okay, right. That is the steady state. Initially, this switch has been at position for a long time. Long time means to attain the steady state. Then this will be the condition. Okay, no resistance. There won't be any resistance due to this inductor. So let us denote it as the initial current. Now let us evaluate the initial current. We know that the current is equal to simply voltage divided by the resistance, that is equal to 5 ampere. 5 ampere current is flowing steadily through the circuit when the switch is at position 1 after a long time. Okay. Now let us take the next condition when the switch is moved from position 1 to position 2. Now let us draw the circuit diagram. Okay. Now when the switch is moved from position 1 to position 2, this is the situation. Now the circuit is facing here. Now the circuit is get connected with 40 volt voltage source. Okay, right. 40 volt voltage source only, and the remaining resistance and inductor is also there. The current flowing through the circuit at that time is known as I of t. Okay, now let us mark that also. We have to evaluate the current I of t at this time. We got three cases. This is the case when the switch was at position 1. Okay. The moment when we put the switch into contact position 1, and this is the case after a long period of time. Now the effect of inductance is over because it is because of the property known as self-inductance. And finally we moved the switch position into position 2. Now this is the situation. Switch is now connected to 40 volt voltage source, and IT is the current just starts flowing through the circuit. Okay, right? Let us apply the KVL, Kirchhoff voltage law, in this equation. We will be getting 40 minus I of t into resistance. That is 4 minus, what about the voltage across the inductance? That is not I of t into L. That is voltage across the inductor is L di by dt. In this case, di of t by dt. That is the voltage drop across the inductor. Okay. Now let us write it as what is L here. L is the inductance. It is 0.2 Henry. So L d I of t is the current flowing through the circuit divided by d of t. Okay, that is equal to 0. Now let us apply the Laplace transform on both sides. Now take Laplace transform on both sides. Laplace transform on both sides, then here we are getting Laplace transform of 40, that minus LT of this one 4I of t minus LT of this 0.2 di of t by dt, that is equal to 0. Okay. 40 is a constant, so let us take it outside. 40 into, then Laplace transform of 1 is there. Okay, minus this 4 can also be taken outside. 4 into Laplace transform of I of t, then minus again this point 2 can also be taken outside, then Laplace transform of di of t by dt, that is equal to 0. Here let us put the equation I of 0 as equation number 1, and later let us mark it as equation number 2. Okay, right. Now we need to refresh some concepts. What is the Laplace transform of 1? That is equal to 1 by s. This is equal to Laplace transform of u of t. Okay, right. Then what about the Laplace transform of I of t? That is equal to I of s. And what about the Laplace transform of a derivative term that we have discussed earlier in my previous video? under the topic initial value theorem and final value theorem, we applied a result, time differentiation property. Okay, right. This is equal to s into I of s minus I of 0. Okay, right. This is known as time differentiation property. By time differentiation property. Okay, right. Now let us mark these equations as equation number 3. Now substituting equations 3 into equation 2, then we have 40 into Laplace transform of 1 is equal to 1 by s. Okay, right. 1 by s minus 4 into Laplace transform of I of t, that is equal to I of s, minus 4 I of s, then minus 0.2 into what about LT of this one, that is equal to s into I of s minus I of 0. As we have multiple terms here, we have to put the bracket, otherwise that will cause an error. Okay, then the minus I of 0 equal to 0. Then what about I of 0? I of 0 equal to 5 ampere from equation 1. Okay, here we have already got the result as I of 0 is equal to 1. Okay, right. Now let us put the value of I of 0 into this equation also. Now what we are getting is 40 by s minus 4 into I of s minus 0.2 into s I of s minus 5 equal to 0. Now let us expand the brackets. So 40s minus 4 I of s minus 0.2 s I of s minus 0.2 into 5, that is equal to 0. Here we have I of s common in second and third terms. So now let us take I of s common and let us put it outside. Then we have I of s into 4 plus 0.2 s. Okay, minus, could you understand why I put plus sign here? It's because when we expand the bracket, we have to get the exact terms as above. Minus I of s into 4 gives minus 4 I of s. Again, minus I of s into this one gives minus term here. This minus into plus become minus here. That's why I put plus sign here. Okay, right? Now minus 0.2 into 5 is equal to 1. Sorry, here I have made a mistake. 0.25, when the moment when we expand the bracket, we have to multiply, we have to consider the sign also. Minus into minus become plus here. I forgot to do that. Now I corrected it. Here also plus 1. Okay, now let us take this term to the right hand side. 40 by s plus 1 in the left hand side, and now I am taking this to the right hand side. Then this minus become plus I of s into 0.2 s plus 4. Therefore I of s will be equal to this term 40 divided by s plus 1 all divided by this term 0.2 s plus 4. Okay, right. Now let us rearrange this equation by multiplying with using LCM. Then we get 40 plus s divided by s whole divided by 0.2 s plus 4. So rearrange this equation. I of s is equal to 40 plus s divided by s into 0.2 s plus 4. Okay, okay, right. Now let us take this point 2 outside in order to make the coefficient of s is equal to 1. Here the coefficient of s is 0.2. Let us take it outside. 40 plus s divided by 0.2 s into, if we take 0.2 outside, the term remaining here is s, then plus 4 divided by 0.2, as we are taking 0.2 outside. Okay, then it is getting divided by 0.2 here. This is equal to s plus 40 divided by 0.2 s into s plus what about this time? This is equal to 20. Now this is equal to 1 divided by 0.2 and s plus 40 divided by the remaining thing is s into s plus 20 here also. Now what about 1 by 0.2? That is equal to 5. So what we are getting is 5 s plus 40 divided by s into s plus 20. That is our I of s. Let us mark it as equation 4. Now we have to take the, in order to find the I of t, we can say that just to take the inverse Laplace transform on both sides. Before that we have to split the right hand side using partial fraction. So let us do that first. Let us apply the partial fraction to the right hand side of this equation. Then we have 5 into s plus 40 divided by s into s plus 20. Okay, right. That can be split using partial fraction as a divided by first pole. What is first pole? That is at s equal to 0 plus b divided by the second pole, that is equal to s plus 20. Okay. Okay, now let us multiply both LHS and the entire RHS term using s into s plus 20. Then we are getting s into, in the left hand side we have s into s plus 5 into s plus 40 divided by s into s plus 20. Okay, right. Now multiply this one using s into s plus 20. The same way, let's multiply the right hand side also, divided by s into, multiply using the denominator of LHS, s into s plus 20. Okay, right. Then followed by plus b divided by s plus 20 into s into s plus 20. S into s plus 20. Okay. Now let us cancel some terms. Here we have s into s can be cancelled, and now here s plus 20 and s plus 20 can be cancelled. Now the remaining term in the left hand side is 5 into s plus 40, that is equal to a into s plus 20, then plus b into s. Okay, let us mark it as equation number 5. Find the values of a and b. Okay, so let us substitute first s equal to 0. S equal to 0. Substitute s equal to 0 in equation 5. Okay, then we are getting 5 into is equal to 0 in this equation. 0 plus 40, that is equal to a into 0 plus 20. Okay, plus b into s equal to 0. Okay, now we have 5 into 40 in the left hand side and a into 20, that is 20a. b into 0 becomes 0. Okay, right now a will be equal to 5 into 40 divided by this 20. Okay, right, that is equal to 10. Now the value of a is equal to 10. Let's mark it as equation number 6. Similarly, now substitute s equal to minus 20 in equation 5. On substituting s equal to minus 20, as we have s plus 20, we have to find s plus 20 equal to 0, so s equal to minus 20. That is what we are going to. S plus 20 equal to 0, s equal to minus 20. That's what we are going to substitute here. Okay, now substituting s equal to minus 20 in equation 5. Okay, what is equation 5? This is our equation number 5. Okay, now we have 5 into, instead of s, let us replace here with minus 20 plus 40 equal to a into minus 20 plus 20 plus 20 plus b into s, so b into minus 20. Okay, right. Now here we have 5 into minus 20 plus 40, 20, that is equal to a into 20 plus 20, minus 20 plus 20 becomes 0, plus b into minus 20 become minus 20 b. Okay, now b is equal to 5 into 20 divided by minus 20. Okay, right. So we have b equal to minus 5. b equal to minus 5. Let's mark it as equation number. Next equation is 7. Okay, now let us substitute the values of both a and b here. Then we will be getting 5 into s plus 40 divided by s into s plus 20. Okay, 5 into s plus 40 divided by s into s plus 20, that is equal to a into, instead of a we can use 10. Okay, right. So let us put here a divided by s, then followed by plus b divided by s plus 20. For the sake of convenience, let us mark it as equation p. Okay, now we have to edit here on substituting equations 6 and 7. 6 and 7 in equation p. Okay, let's avoid the confusion. I'm substituting equation 6 and 7 in equation p here. Okay, we will be getting, instead of b, we can write it as minus 5 divided by s plus 20. Okay, right. That is 5 into s plus 40 divided by s into s plus 20, that is equal to 10 by s, plus into minus become minus 5 divided by s plus 20. Okay, here 5 into s plus 40 divided by s into s plus 20 is equal to I of s. Okay, right. So let us replace this one with I of s by equation 4. For this one is equal to I of s. Then I of s equal to 10 divided by s minus 5 divided by s plus. Okay, right. Now taking inverse Laplace transform on both sides, we are getting here inverse Laplace transform of LHS, that is equal to inverse Laplace transform of the first term of RHS, then followed by minus, and again inverse Laplace transform of second function f divided 5 divided by s plus 20. Okay, right. Now we found in our previous video that the the Laplace transform of u of t, that is equal to 1 divided by s. Okay, right. Then conversely, we can say that this Laplace transform of 1 by s, that will be of course equal to u of t. Okay, right. Then again, we found in the previous video that the Laplace transform of e raised to minus at u of t, that is equal to 1 by s plus a. Then conversely, here also we can say that inverse Laplace transform of this one, 1 by s plus a, that will be of course equal to e raised to at of e raised to minus at of t. Okay, right. Then we can say that the Laplace transform of a continuous time signal I of t, that will be equal to I of s. Okay. And conversely, here also we can say that the inverse Laplace transform of this one, I of s, that will be equal to I of t. Then now let us mark this equation as equation number 7. Okay, right. Now let us take this one as equation 8, then this one equation 9, and finally the last equation. Let us put it as equation number 10. Now let us rearrange this equation number 7. Okay, just inverse Laplace transform of I of s, that is our LHS. Okay, right. Then this 10 is a constant, so let us take it outside. Now we are getting is 10 into inverse Laplace transform of 1 by s. Then minus, here also 5 is a constant, so let us take it outside. Then we are getting 5 into inverse Laplace transform of 1 divided by s plus 20. Okay, right. 1 divided by s plus 20. Okay. Now substituting, so now let us substitute equation 8, 9 and 10 into this equation. What is ILT of I of s? Like ILT of I of s is equal to I of t. So now let us replace this one with I of t. Okay, right. Equal to 10 into, what about ILT of 1 by s? By equation 8, ILT of 1 by s is equal to u of t. 10 into u of t. Then put a minus 10 here. Then find, what about ILT of 1 by s plus 20? Just take a look over here. This one, ILT of 1 by s plus a is equal to e raised to minus at of t. Here we have a equal to 20. Okay, then just replace a with 20 here also. So ILT of this one is equal to e raised to minus 20. Okay, right. Minus 20, then u of t. That will be the current flowing through the circuit as per our question. Okay, this is the current flowing through the circuit, and the expression we are getting is I of t is equal to 10 of t minus 5 raised to minus 20. Sorry, I forgot to put a t here, and this will be our answer. Okay, thank you.